All right, good afternoon. Today we're going to talk about section 3.6, derivatives as rates of change. So usually we like to talk about one-dimensional motion in this class when we do our examples, whether that's displacement of a car, displacement of a stone, displacement of a potato being thrown. And we use this position function, and we're curious what the position function actually tells us. So here I've got a little cartoon, and I've got a little car driving away from a house. And it says that at time 0, the position is 0. At time A, the position is f of A, and at time A plus delta t, our position is f of A plus delta t. And the difference between those 2 points is delta t, the time elapsed between when the car was at position s equals f of A and when the car is at s equals f of A plus delta t. So position is measured relative to a reference point, that is s equals 0. So where the car is, maybe we say that s equals 15, that's with respect to an original position s equals 0. And it's always important that we know where that position is, where that initial reference point is. And so I'm going to try and make a point to really emphasize that in the next coming examples. And then we talk about displacement. And displacement is the difference between where an object currently is and where the object was as time elapses. So just like we said before, delta S, the displacement of our object, is f of A plus delta t minus f of A. So now we can talk about average velocity. And again, the average velocity is going to be the displacement over the time elapsed. So we have delta S over delta t, where delta t is elapsed time, and delta S is f of A plus delta t minus f of A. And we can find the instantaneous velocity by taking the limit as delta t goes to 0. And that's exactly what we do to get f prime of A, or the instantaneous velocity. And again, it's really important that you remember exactly where all these things come from, because we use them so often and they're so deeply intertwined with one another. So the average velocity, when we take the limit as delta t goes to 0, equals the instantaneous velocity. Now, here's the relationship between velocity, speed, and acceleration. The velocity at a time t is v equals ds over dt, or f prime of t, while the speed is the absolute value of velocity. And we remember the absolute value, we drop any negative signs. So what we learned with speed is how fast you were going, but not necessarily what direction you were traveling in. If I say west is negative and east is positive, and you were traveling 90 miles an hour west, then I would only know that you're traveling 90 miles an hour. I wouldn't know if you were traveling west or east if you just gave me the speed. Furthermore, the acceleration at time t is the second derivative, or it's the first derivative of velocity. And so we get dv over dt, or d squared s over dt squared, or this f double prime of t. All of these are interrelated, and it's important to keep in mind these interrelationships when we work with word problems. And especially if you have not taken college physics yet, you'll see a lot of this in college physics. So let's start with an example. Assume a police station is located along a strictly east-west freeway. At noon, time equals 0, a patrol car leaves the station headed east. So in this one, when time equals 0, our position equals 0. We're starting at the station, and that's exactly what this means on this graph. The position function of the car is s equals f of t, and we're measuring as time elapses on this bottom axis. We're measuring the position in miles from the station, where positive is further east of the station and negative is further west of the station, at whatever time you are after noon. So let's describe the location of the patrol car during the first 3.5 hours of this trip. So That was really silly. The trip lasts exactly 3.5 hours. So let's break it up into a few segments. I'm going to break it up like this. Maybe I need a different color. So we see from time equals 0 to time equals 1.5, our position is increasing. That means we're getting further away eastward from the police station. So from 0 to 1.5, we're going east. Then something curious happens. 1.5 to 2, we stay in the same position. We stay 80 miles away from the police station. So we're stopped. And then we see that our position is decreasing. That means we're getting closer and closer to the police station until we eventually go negative. And we establish that when you're negative, you're further to the west. So from 2 hours to 3.5 hours, we're headed west. And we can break this down even further and see what exactly our slopes are at any given time. And it kind of looks like the slope here is like that, and the slope here is kind of like that. So we see we have regions where we're slowing down or speeding up, where our slope isn't constant. And those would be regions where we're going from 0 miles an hour to maybe 15 to maybe 30 to however many miles an hour the cop car is traveling. So now let's get into the nitty-gritty. Let's calculate the displacement and average velocity of the car between 2 p.m. and 3:30 p.m. So I'm going to mark those here. And at 2:30, we're just starting to head west. And so at 2:30, we've traveled our displacement is going to be S final minus S initial. Our final position is at negative 20. Our initial position is at 80. So delta S equals negative 100 miles. And let's think about why that makes sense. It makes sense because we've traveled 100 miles, and in our coordinate system, we've traveled west, which means we're getting first towards the police station headed westward, and then beyond the police station headed westward. So that negative sign really just means west. And then the average velocity of a car is going to be delta S over delta T. So we have negative 100 miles over 1.5 hours, which means in general we traveled about 66 miles per hour headed west, and that's what that negative sign means. Finally, at what time is the instantaneous velocity greatest as the car travels east? And so we're asking, at what time is the slope of the tangent line the steepest as the car travels east? Now I'll give you a hint. We're only concerned with this first portion of this graph. And we really have, again, 3 little sectors. We've got from 0 to 0.5, where we're increasing our speed, from 0 to 5, where we're traveling at a constant speed, and from 1 to 1.5, where we're decreasing our speed. So at the time our instantaneous velocity is greatest is going to be in this middle sector, and that's when the slope of our tangent line is going to be steepest. So let me write that. And that's it for that question. So let's move on to another question. And this is example 2. So suppose a stone is thrown vertically upward with initial velocity of 64 feet per second from a bridge, which is 96 feet above a river. The position of the stone after t many seconds is s of t equals negative 16t squared plus 64t plus 96. And we want to find the velocity and the acceleration functions. So the first thing I'm going to do is actually draw what this graph looks like. And because we start 96 feet above the bridge, we're going to start there. So what we have is a stone is thrown upward. It reaches a peak where velocity equals 0, and then it falls back down to Earth and eventually lands in the river. So at time equals 5, or at a little bit past time equals 5, we've landed back in the river underneath the bridge. So finding the stone's velocity is as simple as finding the first derivative. So v of t, let's remember our rules, negative 16 times 2 times t to the 2 minus 1, which is 1, plus 64 times t to the 0, which is 1. And then because 96 is a constant value, we drop it. So really, this looks like negative 32t plus 64. And then acceleration is just the derivative of velocity, so we do it again. Negative 32, we drop the constant. And I've added units just to make things make more sense. Our position function is measuring our position in feet as height above the bridge. The velocity function is measuring how fast our stone is traveling in feet per second, and the acceleration is measured in feet per second squared. So now I would just really want to get into drawing these pictures. So we start at about 64. And our position and velocity diagrams look like that, where at time equals 2, at time equals 2, or just thereabout, our stone reaches its peak. And we see that in the velocity diagram as our slope crosses, our line crosses the time axis. So as our slope is positive, we are traveling upward. As our slope is negative, we're traveling downward. And our slope is decreasing and then getting increasingly more negative. Let's see. Let's move on to the next section. So what is the highest point above the river that is reached by the stone? And we know that this happens when velocity equals 0. So let's solve for t. I'm left with 2 over 1 t. So the stone reaches its peak at time equals 2 seconds. And I did that with some quick algebra. So let's move on to question C. With what velocity will the stone strike the river? So we know that the stone will strike the river when the position is equal to 0. So if we divide everything by 16, we're left with, if we divide everything by negative 16, we're left with t squared minus 4t minus 6 equals 0. And then we just have a quadratic. And I'll go ahead and tell you that our quadratic gives t equals negative 1.16 and t equals 5.16. So let's think about what is going on here with those answers. Somehow we've gotten a negative answer, and that makes sense based on what it means to solve the quadratic formula. But we know that time can't be negative, so we can already go ahead and cross out that answer. So we're left with one answer. Time equals 5 seconds and 16 milliseconds. And that makes a whole lot of sense. And if we go back to my graph, we saw that we hit the ground just after 5 seconds, so we're able to fill that in. So these two examples aren't necessarily exactly like the homework questions you have for this section, but I didn't like many of those questions, didn't think that they would be good as example questions for showing you exactly the interplay between position, velocity, and acceleration. So I chose to do some examples out of the book instead. So moving on. Next, we've got growth models. So populations, prices, and many other things grow over time, and we measure the quantity of interest, whatever's growing, with P equals F of T. We typically use P because P means population, and a lot of the times we're talking about the population of maybe bats in a forest or, I don't know, snails, wherever snails live. But this figure is pulled from your textbook, and it's actually about internet growth. So P represents the number of people who are using the internet between 2000 and 2015. And we see that we've got something that kind of looks like a quadratic. And in fact, when we go to write this down, we see that a reasonable fit for our data is P of T equals 6t squared plus 98t plus 431.2. So we know that that's a quadratic. We know that this is a quadratic. Our red dots are data points. Our black line is the line of best fit. We know that this is a quadratic. So we can expect dp dt, the growth in time of the growth rate of internet users, so how many more people are joining each day, to be linear. Because the derivative of a quadratic function is linear, the derivative of a linear function is constant, etc., etc. So this is just to show you that there's other things we can measure and use calculus to talk about. And many of you will go on to use these concepts, whether or not you use it directly or indirectly, whether or not someone just hands you a textbook and says, look it up, or whether you're actually doing the calculus every single day. So the average growth rate of change is going to be delta P over delta T. So the change in population or the displacement, so f of a plus delta T minus f of a over the elapsed time, which is delta T. And we get the instantaneous growth rate of change, dp dt, by taking the limit as delta T goes to 0 of delta P over delta T. And that's it for